Good morning. Today I'm going to present about the review of sustainable CO2 storage as aquifer using hybrid ANN and numerical model across different trapping mechanisms. The paper information, the author is Shirif E. The affiliation is the University of Regina. The journal is Sustainability from Switzerland. The year is 2025. The main keywords are carbon storage, sequestration, the artificial neural network MATLAB, reservoir simulation CMGM, Saline aquifer, CO2 trapping, and sustainability. In the contents, first we have the introduction, is separated into the research background and research of the research background. First, we need to understand why the CO2 storage have relation to the tropic mechanism. First, the atmospheric concentration of CO2 has increased dramatically in these years, driving to global warming and climate-related impacts. So the carbon capture storage is a mitigation strategy. As you can see here, we can find deep saline aquifers onshore and offshore. And commonly, they came with the cap rock that keeps the CO2 storage. Then this accurate prediction is challenging because of the complex trapping mechanisms that are these ones: the structural trapping, residual trapping, solubility trapping, and linear trapping in that order. And that's how it came this numerical simulator that, for example, the CMGM, that are powerful, but they are expensive for the large uncertainty analysis. The objective is the hybrid framework, combining the CMG numerical simulations plus the artificial neural network, and predict the CO2 storage capacity across these multiple tropic mechanisms. First, they evaluate the CO2 storage capacity in the saline aquifers, integrating these numerical reservoir simulations, then develop and validate an artificial neural network that predict the CO2 storage, and finally reduce the cost and simulation time with high predictive accuracy, trying these ANN in different types of algorithms. The methodology is divided into 5. First is the numerical reservoir modeling. They compose a 3D compositional model of a saline aquifer into the CMGM. The key model is that this model domain consists in 300,000 grid cells. The CO2 injection is on the single vertical well that is shows here, and is perforated in the lower layers of the reservoir. The injection includes a maximum bottom hole pressure to maximize the CO2 injection rate, and also the simulator modeling a supercritical CO2 state. In the time span is set for 200 years to see how the trappings work. Then they pass to the step of sensitivity analysis and data generation. Here is a histogram of what are the key geological and operational parameters as the inputs, as porosity, permeability, injection rate, and how it varies between the different analyses that they make. In the case of reservoir thickness, as you can see here, most of them show a thin simulated aquifer to explore if the thickness have something to do with the formation. There is sensitivity come from 3 to 10, as you can see here. Then is the hysteresis coefficient. This is stronger related to the residual trapping. This determines if there's going to be a residual trapping in the pores of the reservoir. So as you can see here, it's mostly with higher values to make higher retention of the CO2 into the pores. Here. Then is the bottom hole flowing pressure. This is concentrates around high pressure, typically to maintain the CO2 into a supercritical state. Then is the CO2 injection rate. This covers to low to high injection scenarios. Most of them are like low scenarios because of the pressure of the bottom hole to keep the CO2 into a supercritical mode. Then is the horizontal permeability. This is wide range. This allows the CO2 mobility into these different states of trapping. But in the case of the permeability, vertical permeability, this remains relatively low from 0.0 to 0.5, limiting the vertical migration and enhancing this confinement. And then the porosity. The porosity is centered in moderate to high values to ensure sufficient pore space for the storage. And then is the aquifer pressure, reservoir pressure, that this is a realistic deep reservoir conditions that favor the CO2 density and solubility. Then on the case of the aquifer volume, it shows mostly large range that support the long-term CO2 dissolution of the brine. This helps to the CO2 dissolve. And then these are the histograms of the outputs. This is the CO2 supercritical. It remains in low to keep this state into the simulation. Then the CO2 structural, as you can see here, shows less numbers. It depends mostly of the volume of the reservoir is the principal state. Then the residual, it depends mostly of the high series coefficient. So remained also in low because the high series coefficient try to keep it into a big CO2 residual space. Then is the CO2 mineral trapping. This one remains also in low because these mineral trappings occur in a long time terms. It reacts with the minerals, and the CO2 dissolved depends mostly of the salinity of the water. So then the next step is the CO2 trapping mechanism quantification, how they determine these outputs. In the supercritical CO2, it's computed is directly from the simulator. The volume of the supercritical CO2 is equal to the sum of porosity per the volume of the cell and the saturation of the CO2. Everything comes from the CMG. Then the structural trapping is to identify, especially from the simulation by tracking the CO2 saturation. Typically is when the plumb migration is stabilized and is a subset of the volume of the supercritical CO2. Then is the residual trapping. This residual trapping occurs when the CO2 becomes immobilized. It depends most of the high series coefficient. That's why here, first of all, the saturation of the CO2 in a residual trapping is equal to the function of high series coefficient. It means that it depends mostly of the time into this coefficient. If it's a more coefficient, it means that the CO2 is gonna be trapped on the pores, and if it's low, it means that there is not gonna be like residual. This is trapping. Then this volume of the residual trapping is equal to the sum of the porosity per the volume of the seal per this saturation of the residual trapping. Then is the solubility trapping. The simulator calculates this using a CO2 brine equilibrium relation because it depends mostly of the brine. So the volume is equal to the sum of the volume of the brine per the concentration of dissolved CO2 into the brine. Then is the mineral trapping. The simulator tracks mineral precipitation kinetics, that it means what is the reaction of these different chemical reactions into the CO2 with other minerals, and the volume is reported as equal the sum of the precipitate carbonate mass that are the result. Then they developed the ANN model, generate clean data. They normalize the data that they take from the CMG into an artificial neural network in the MATLAB. The steps to follow is prepare the data, model setup. As you can see here, the inputs are reservoir pressure, aquifer volume, all the ones that we take in consideration in the beginning, and the outputs are 5: the supercritical volume, residual trapping, structural dissolved, and the training is trained and optimized to capture these nonlinear relations, and they also put a validation of the model performance. Into the validation and evaluation, they try different ANN training algorithms that they evaluate the variation regulation, scale conjugate gradient, and Lavenger Marquardt. In the case of variation regulation, this helps achieve a better generalization. It works better with fitting the data and keeping the model simple, and it's uses in cases for the regression problems are complex, have complex patterns. Then the scale conjugate gradient, this algorithm doesn't require like a lot of iterations, try to make it faster than other algorithms, and is advantageous for training large neural networks and handling data sets that are computational, are bigger. And then is the Levenberg Marquardt. This is often converts to a solution that have a smaller sum of squared errors. It's effective for pattern recognition and time series prediction. And they evaluate this model using the statistical metrics that is the coefficient of determination and the mean squared error by comparing this ANN prediction. The results are, first of all, what is the correlation? They present this heat map about all the correlations between the outputs and the inputs. In the case of the CO2 supercritical, it have a strong relation with the CO2 injection rate. In the case of the CO2 residual, it depends mostly of the hysteresis coefficient. Then the CO2 structural, CO2 mineralized, and CO2 dissolved depends a lot of the aquifer volume, because this one enhances the CO2 dissolution, mineralization structure, and also the permeability influence into the CO2 mobility and structural accumulation. In the case of the ANN evaluation, the Levenberg Marquardt achieved the best performance. As you can see here, is achieves a coefficient of determination of 0.96. And here there is the error histogram that determines if it's more close to 0, and most of the cases are close to 0, as you can see here. And that means that the model successfully predicts all major trappings simultaneously, and unlike previous studies. So the main conclusions are that the hybrid CMGM and ANN framework provides an accurate and computational efficient tool for this CO2 storage assessment. They incorporate, as you can see here, data generation of the CMG, data training and validation with these 3 algorithms, and then the improve a model of CO2 storage and sequestration potential. This approach is going to support rapid screening, optimization of different CSCs projects, and the methodology represent a scalable and sustainable solution for this CO2 storage planning that include this trapping mechanism. Thank you. Mm, please? Yes, it was with tropic